In our digital world, data storage and transmission are critically important. We use linear algebra and finite fields to ensure data integrity. Take this compact disc. If you scratch an old vinyl disc, then you ruin the record. You will get terrible cracking sound when you try to play it. So this compact disc has an additional layer of protection. If you scratch it, then it will still play perfectly. Well, of course, if you don't scratch it too badly. How can this be made possible? So how can we organize this extra layer of protection so that if we erase some data written on this disk, we do not lose information? So this means that the recording will play perfectly. So this is achieved using error-correcting codes. So we encode information with some redundancy, so that if part of this data is lost, we can still completely recover information encoded on this device. A naive way of creating error correction is to take data and write it 3 times. So if one of these 3 copies is damaged, then we can use 2 other copies to identify the correct version and to recover the data. But we want to do it in a much more efficient and much more clever way. Let's see how can we use linear algebra to organize error correction. The oldest and simplest idea here was parity check. Suppose we have n bits of data. So x1, x2, ... xn, where each xi assumes values 0 and 1. So this is a string, binary string, so string of 0 and 1s. From the point of view of algebra, so each xi belongs to the field z2. Now, what we do is, so we add 1 extra bit, so which is called parity check bit. So we augment this data with 1 extra bit, which is calculated xn plus 1 as x1 plus x2 plus xn mod 2. So this is a linear equation. So in fact, we can write this linear equation as x1 plus x2 plus xn plus 1 is equal to 0, right? So in Z2. So here we bring everything to one side, and the sign is plus and not minus, because over Z2, x and minus x is the same thing. Now, what we transmit is not the n bits of information, but we transmit these n plus 1 bits. When we receive n plus 1 bits, on the other end, we verify whether this equation holds. So if this equation holds, so this string passes the test. If it doesn't hold, if we get 1 in the right-hand side, then this indicates the failure, and this means that there was an error in transmission. However, so here we cannot say in which bit do we have the error. So here we just know that the error had occurred. What we want to do next is we want to organize a much cleverer scheme. So we want to find a way how to implement not just error detection, but an error correction. We will discuss today the Hamming code. This is the most elementary error correcting codes. So in practice, today we use far more sophisticated and far more powerful error correcting codes that use way more advanced algebra. But the main idea of error correcting can be seen with the Hamming code as well. Consider the following system of linear equations over Z2. So here we have 3 equations and 7 variables. And these variables assume values in Z2, and all equalities are also considered to be as equalities in Z2. Let us solve this system. Well, first step that we do is we create the matrix of this system. So the matrix will be, so for the first equation we have coefficient 1 for x1, then we have no x2 and x3, so we have 0 and 0. So then we have x4 has coefficient of 1, x5 has coefficient of 1, there is no x6, and we have x7. And we have 0 in the right hand side. For the second equation, so there is no x1, we have x2, no x3, we have x4, no x5, and we have x6 and x7, and 0 in the right hand side. And for the last equation, we have no x1, no x2, we have x3, no x4, we have x5, x6, x7, 0. So this is the matrix of this system of linear equations. Now, luckily for us, this matrix is already in reduced row echelon form. Right? So here we can clearly see the pivots. Right? So these are our leading ones, and so we see that this matrix in reduced row echelon form, so writing a solution is very easy. So we have to identify leading variables and the free variables. So the leading variables are the variables that correspond to pivot columns. So in this case, so these are x1, x2, and x3. And all other variables are free variables. So this will be x4, x5, x6, and x7. Now, how do we solve the system of equations? So we assign parameters to free variables, and then we express leading variables from the system. So let's assign parameters. So we have x4 is s, x5 is t, x6 is r, and x7 is u. And so for leading variables, we can express them using these equations. So if we bring this to the right hand side, then this reads x1 is equal to negative x4, negative x5, negative x7. But over Z2, so minus x and x are the same thing, right? So because x plus x is x times 1 plus 1, but 1 plus 1 over Z2 is 0. So this is x times 0, which is 0. So x1 is going to be x4 plus x5 plus x6. Or in terms of these parameters, so this is s plus t plus r. So likewise, so x2 is from this equation, it's x4 plus x6 plus x7. So this is s plus r plus u. And the last leading variable, x3, is x5 plus x6 plus x7. So this is t plus r plus u. So now we have 4 free parameters, and we expressed all of our variables in terms of these free parameters. Let us ask a question. How many solutions does the system of equations have? So here we have 4 parameters, and each of these parameters can assume value 0 or 1. So the total number of possibilities will be 2 to the power 4. So this is the number of solutions. So because we have 4 parameters, and each parameter has 2 possibilities. So this is equal to 16. Let us look at this situation from the point of view of data science. So here we say that a solution x1, x2, x3, x4, x5, x6, x7 of this system of linear equations is called a code word. Now, how can we describe code words and their structure? Well, linear algebra tells us that we can assign arbitrary values to the last 4 bits. So this means that these 4 bits here are information bits. We can assign them any values we need. Once we specified what are our information bits, then the first 3 bits will be identified by them using these relations. And so these are called parity check bits. So this means that the first 3 bits in the code word are predetermined by the information part, which is the last 4 bits. Let's consider an example. A humming code word encodes 4 bits of information. And suppose our information bits are 0, 1, 1, 0. These are our bits x4, x5, x6, and x7. Next, to form a code word, we add 3 additional parity check bits, x1, x2, and x3, where the values of these are determined from our solution, right? So x1 is x4 plus x5 plus x6 plus x7. x2 is x4 plus x6 plus x7, and x3 is x5 plus x6 plus x7. So the values of these bits will be x1 is x4, that's 0, plus x5, that's 1, plus x7, that's 0, 0 plus 1 plus 0 is 1. x2 is x4, which is 0, plus x6, which is 1, plus x7, which is 0, 0 plus 1 plus 0, that's 1 again. And x3 is x5, 1, plus x6, 1, plus x7, 0. 1 plus 1 plus 0, that's 0 in Z2. And we use the same information bits. So this is our code word here. Now, for each 4 bits of information that we have, we add extra 3 bits and we transmit 7 bits of information. On the other end, so when we receive 7 bits, so what we do is we take them and we plug them into the system of equations. If we receive zeros every time for every equation, then this would mean that what we received was a code word. And so then we discard the first 3 bits and we keep the 4 information bits. But what will happen if we have an error during transmission? Suppose during transmission an error has occurred, and what we received is not the code word that was sent, but something else. So suppose what we receive is 1100, and imagine that here this bit comes in correctly as 0 and 10. So then once we take these 7 bits and plug it into the system of equations, then the right-hand sides will no longer be 0. And this will indicate that an error has occurred. But what we want to do is we want to do better. We want not only detect the fact of occurrence of the error, but tell in which bit the error is and correct it. Let's see how can this be done. We take this word, 7-bit word, and plug it into the system of equations. So we get x1, which is 1, plus x4, which is 0, plus x5, which is our incorrect bit 0, plus x7, so this is 0, and so this is equal to 1. Now, in the second equation, we have x2, which is 1, plus x4, which is 0, plus x6, which is 1, plus x7, which is 0. So this is equal to 0. And the last equation is x3, which is 0, plus x5, which is 0, plus x6, which is 1, plus x7, which is 0. So this is equal to 1. Now, what we do is, so we look at the right-hand sides. So we have 1, 0, 1. And we go back to our original matrix, the coefficient matrix of this system of equations. And we look up, where do we see a column 1, 0, 1? So we see this column right here. And that is an indication that the error had occurred precisely in column number 5. And so the correct code word will have 1, 1, 0, 0, and we change the bit number 5. So this will be 1 and 1, 0. So in this way, we recover the correct bit in position number 5. Now, why did it happen? So why this method works like this? So let's see. What was the reason why we got 1s in the right-hand side here? So we got 1s because of the incorrect value of x5. So where is x5 here? So here we have x5 is this value. Then the second equation has no x5. And in the last equation, so our x5 is here. And so what we see is that if an equation does not have the bit that contains an error, then that equation will be satisfied. And those equations that do depend on the unknown that contains an error, so those equations will fail, and we have 1s in that right-hand side. So this means that when we plug in what we received in our system of equations, so if the result is all zeros, then this is a code word. But if the result is non-zero, so the locations of ones will indicate which equations contain the variable with an error. And these are exactly the column information from our coefficient matrix, because the first column tells us which equations contain variable x1. The second column tells us which equations contain the variable x2. And the fifth column tells us which equations contain variable x5. And the nice thing about this coefficient matrix is that all columns in this matrix are distinct. If we receive any combination of 3 bits, so there will be a column with precisely the same combination of 3 bits. And in this way, if one error has occurred, we can find its location and correct them. If we have more than one error occurring in the code word, then of course this method will fail. So this Hamming code has capability of correcting a single error. But there are far more advanced codes that are being used today that can correct more than one error. Error correcting codes are used everywhere where we have data storage or data transmission. The areas of applications range from hard drives to QR codes to deep space communications. When NASA needs to send data to Mars rovers, the data is encoded with error correcting codes that use linear algebra over finite fields.